Okay, class. Now we want to look at a limit that, how do we evaluate the limit? Okay, a limit that does exist or does not exist. All right. So as we done in the one variable case, when you evaluate a limit, you can plug in a number unless the numerical value does not exist. So we look at an example right here. Show that the limit does not exist. Obviously, if you plug in 0, 0 for the denominator, x squared plus y squared, and then it's undefined. So how do we do this? So we approach it a very different way. Okay, we let approach x along the x-axis first, and then y should be 0. So that gives us what? As the expression here, if y give us 0, we'll have f of x0, which is equal to x squared minus 0 squared over x squared plus y squared, which is equal to 1. So along the x-axis, the function value is a constant value, 1. And if we look at the picture here, okay, follow the red dotted line there. It approach as x approaches right here, approach to 0 along x-axis, the function remains a constant 1. So we say the limit equals to 1. What about the other way around? Look at the y value here. Okay, obviously it's below. Look at the value; it's below the below the xy plane. If you look at the next one, if we approach along the y-axis by putting x equal to 0, and again we look at here, 0 y so, or not. Okay, we get 0 minus y squared over y squared, you get negative 1. It's a constant value, as you can see. Follow the red dotted line right here. That is goes to negative 1. So as a result, you can see as x along x-axis, when x approaches 0, the function value is 1. Along y-axis, when x equals to 0, the function value is negative 1. They don't go to the same place. All right, so since f has two different limits along the two different lines, the given limit does not exist. Okay, as long as you can find one example that the two function values do not match along two different paths, then the limit does not exist.